In the today's session, we will discuss about the testing of contrast. First of all, we will see what is a contrast. If we are having k number of populations and the means of these k number of populations given as mu1, mu2, mu3 up to mu k. And if we are defining any linear combination and we are naming it as the capital L, uppercase letter L. It is a linear combination of these mu1, mu2 up to mu k values in the form where L equals summation I goes from 1 to k ci times mu I. We are saying this form as a linear form, and we are saying this linear form as a contrast if this condition is satisfied. The condition is summation of ci, I goes from 1 to k, should be equal to 0. It is quite like this. Now think about here you may have mu. I will take this mu1, mu2 and mu3. Think we are having three treatments and the means of these three treatments are mu1, mu2 and mu2, mu3. If I need to make a linear combination, I can make this linear combination as mu1 minus mu2 minus mu3. This is just a linear combination. This is a linear combination. Then here we can see where I equals 1, we are having ci equals 1. Here we are having 1, here minus 1, here minus 1. Likewise, we are having the ci value. But this is just a linear combination. This cannot be said as a contrast. It is because once you check for the summation of ci value, then here the sum this ci value or the c1 value is 1, then c2 value is minus 1 and c3 value is minus 1, and the summation of these three values does not equal to 0. Since the summation of the ci values does not equal to 0, we cannot say such type of linear combination as a contrast. Now think about if the contrast is given as 2 times mu1 minus mu2 minus mu3. In such a situation, we will check for the summation of ci values. Here, the c1 value is now 2. Then you can see that c2 value is minus 1, c3 value is again minus 1. Therefore, now you can see that here the summation of these three values are equal to 0. Therefore, now we can say that L is a contrast. Therefore, L is a linear function, and if it satisfies the condition summation of ci equals 0, then we are saying such linear combination as a contrast. And if we have build up a contrast, then we can test for the hypothesis. The hypothesis that we are used for testing contrast is null hypothesis. Summation of I goes from 1 to k, ci mu I equals 0 given constant, versus alternative hypothesis, summation of ci mu I where I goes from 1 to k does not equal to 0 given constant. This is the hypothesis that we are testing for contrast. Hypothesis that we are testing for contrast. And now we will see how we can perform this hypothesis testing. Since this is our hypothesis, we are using this f value, calculated f value, as the test statistic, and it is defined by the contrast sum of whiskers. Contrast sum of whiskers denoted by SSL divided by MSE. Actually, this is uh, mean whiskers for contrast. Even though it is mean whiskers, we can replace it with the whisker sum of contrast. It is because in the latter part of this session, you will know that the degrees of freedom of a contrast is equal to 1. Therefore, now think about if you are defining ms, so far we have defined ms by ss divided by the degrees of freedom. Ss divided by degrees of freedom. Now what will happen if this degrees of freedom equals to 1? Then ms divided by ss, ms equals ss divided by 1. Therefore, you can simply say that ms equals to ss. Therefore, if the degrees of freedom equals to 1, then mean square value and sum of squares are equal together. Therefore, based on that concept, we can use the SSL here. SSL stands for the square sum of contrast. Therefore, to find the square sum of contrast, we can use this equation, summation of CIY bar yi bar squared divided by CI squared divided by Ni. CI's are the constants in the linear combination, and yi dot bar is the ith treatment mean, and Ni is the sample size of the ith sample. Therefore, this is what we are used to calculate the square sum of contrast, and once you divide the square sum of contrast by the mean square error denoted by MSE, then you will get this calculated F value. Therefore, once you have a calculated F value, then you have to define a decision rule. Therefore, based on the F table, based on the F distribution, we are defining this decision rule. Therefore, the decision rule is we are rejecting the null hypothesis, or in other words, we can say that we can reject H naught if the calculated F value is greater than the F critical value. Here, the critical value for F would be F1, n minus k 1 comma n minus k at the defined alpha level, Normally we are considering value of alpha equals to 0.05. In generally, we are considering value of alpha equals to 0.05, or at the 5% significance level. And this n minus k, once you deal with the calculation, then you can identify this n minus k is the degrees of freedom. Degrees of freedom stands for the error. This is the actually error degrees of freedom is this n minus k, and here the degrees of freedom of numerator would be 1. It is because if you are defining a contrast, then degrees of freedom of a contrast should be definitely equal to 1. This is one point you have to keep in your mind. Uh, Once you are defining a contrast, degrees of freedom of given contrast is equal to 1. That is why we are taking this critical value as f1 n minus k at the given significance level alpha. Okay, we will go through an example for testing contrast. This is the example that we have considered at the previous sessions. Also, the sulfur content of 5 major coal seams in the particular geographical region. Therefore, again we are dealing with the same example. Therefore, we are having 5 coal seams, and then for each of these 5 coal seams, we have several observations, 7 observations, 8 observations, 9, then 8 observations and 10 observations respectively for the coal seam 1 to coal seam 5. And here we need to first check for this hypothesis. Therefore, we will consider the coal seam in when we are discussing the things with the pairwise comparison. What we have done there was we are testing if we are considering one coal seam, and then we are testing for each of the other coal seams whether the mean values are equal or not. But when we are defining the contrast also should be a meaningful contrast. Therefore, now what we are going to do is, now we are going to test this 1 and 3. combination of these 1 and 3 with the 4 and 5 coefficients. Therefore, now we need to check whether the mean value of the coefficient 1 and coefficient 3 are equal to the mean value or the average value of average sulfur content of coefficient 4 and coefficient 5. Therefore, actually when we go to build up the hypothesis, we can say H naught. What we are going to do test is we need to test whether the mean value of these two equals to mean value of these two. Therefore, what we can do is here, first of all, you can say this is mu1. I will write it here. You can say this is H naught. Therefore, first of all, I need to test the average value of 1 and 3. Average value of 1 and 3 is equal to average value of 4 and 5. Average value of 4 and 5. Average value of 4 and 5. Therefore, now since this H note is just a notation only, therefore, so far we will discuss about this part only. We will just consider about this part only. Therefore, if you see above, now you have defined average value of coefficient 1 and 3 equals average value of coefficient 4 and 5. Therefore, rather than writing your hypothesis in this form, what you can do is in both sides you can have the same value too. Therefore, we can define this as mu1 plus mu3 equals to mu4 plus mu. This is how we are defining. But furthermore, we can develop this hypothesis. Therefore, what we have to do is you can take the terms in the right hand side to the left hand side of this equation. Therefore, we can define the H naught rather than keeping these uh, as two-sided in the both left and right hand side. Therefore, we can take all the terms to one side. Therefore, we will get this as mu1 plus mu3, then minus mu4 minus mu5, and this is equal to 0. Since this is the null hypothesis, then we can define the alternative hypothesis in this form. Therefore, I will say this as mu1 plus mu3 minus mu4 minus mu 5. Since we have used the equal sign, then alternative contains the not equal sign. Therefore, this is how we are defining the hypothesis in the testing for contrast. Therefore, according to the situation that we need to test, we are defining the contrast. Now you can understand in the pairwise comparison, what we have done was we have checked a single treatment with the every other treatments. Sometimes it may be controlled with every other treatment or any given treatment with other given treatments. But once you are constructing contrast, then it is just a treatment combination. Therefore, one treatment combination can be checked with another treatment combination. Therefore, that is the main difference between the pairwise comparison and the testing for contrast. Therefore, since this is the hypothesis that I have prepared, then I will go for the testing of the hypothesis. Therefore, this is what I need to test. It is the average sulfur content of coal-seam 1 and coal-seam 3 are equal to average sulfur content of coal-seam 5 and coal-seam 4 and coal-seam 5. Since we have gone through the same example previously also, then we know about these values. But if these values are not given, then you have to recalculate these values. Therefore, using this table, you can identify the values of each treatment mean. Therefore, the treatment means identified as 1.66, 1.17, 1.46 and 0.4, 0.88, and for the fifth whole same again 0.88. And the sample sizes of each population identified as 7, 8, 9, 8, and 10. And for before testing for contrast, what you have to do is, first of all, you have to obtain the ANOVA table. Therefore, in the previous examples, we have defined the ANOVA table and we have identified the mean square error as 0.1215. Using the previous ANOVA tables, I have obtained these mean values, and based on the data provided, I have identified the sample sizes, and based on the ANOVA table that we have discussed previously, I have obtained this mean square error value as 0.1215. Now we have to identify the appropriate CI value. Now once you see about the null hypothesis, based on the null hypothesis, we can easily identify these CI values. Now you can see that here number 1 appears, there is no numbers. Number 2, 3 calls in 3 appears, calls in 4 appears, and calls in 5 appears. Therefore, the constant in front, or the coefficient in front of the given population mean can be identified as the value of Ci. Therefore, what we can do, what we can take as C1 here, there is a presence of first whole scene. Therefore, we can take C1 equals to 1, and there is no any presence of holes in 2, therefore value of C2 equals 0. Then presence of holes in 3, now value is 1, coefficient is 1. Then holes in 4, then we can say here it is -1, minus times 1 minus 1, then value for C5 is again -1. Now if you need, you can check whether this is a valid contrast. To check whether this is a valid contrast, what you have to do is you have to identify what is the value of summation of Ci. Then you can take this as 1 plus 0 plus 1, then -1 and -1. This plus -1 and this plus -1. What you have to do is you have to add these values together. Therefore, at the end you can see that summation of Ci values are 0. Therefore, we can say that this is a valid contrast. It is because summation of Ci values are now equal to 0. Therefore, if there is any doubt whether the contrast is correct or not, then you can check whether the contrast is correct or not just by adding the Ci values together. Then the summation of Ci values should be equal to 0. Okay, now you have identified all the required details. Therefore, now you can go for calculation of contrast sum of square. Therefore, it is denoted by SSL, and the equation that we have discussed previously can be used to identify the contrast sum of squares. Then it can be written as summation I goes from 1 to k Ci yi dot bar square term divided by summation of Ci square divided by Ni, where I goes from 1 to k. Here yi bars are the sample means and Ni is the ith sample size, and Ci's are the coefficients that we have already identified for each given treatment. Therefore, once you do the substitution for the numerator, we have to get the summation of Ci times yi bar. Then if you consider the first call seam, Ci value was 1 and mean value was 1.66. Then plus, then for the second call seam, there is no such value. Therefore, C2 value is 0. Therefore, if you need, you can insert it to the calculation. Here, since the value is 0, I have not included. If you need, then rather than writing it here, then you can say that this plus, then 0 times, then this value definitely becomes 0, plus, then the third value is 1, mean is 1.46, then plus the fourth coefficient C4 value is -1 into 0.88, plus again fifth coefficient -1 into 0.88, and the addition of these terms should be considered to the power 2, or this we have to square the total. and then this has to be divided by the square term of Ci's divided by Ni. Therefore, first value was Ci value was 1, then 1 square divided by the sample size associated with Ni is 7. Then next Ci squared Ci squared, it is C2 squared. Actually, C2 is 0. I have not included it in the calculation. If you just need, then you can say it as 0 squared divided by sample size associated was N2 was 8. Therefore, 0 squared divided by 8 again gives you the value as 0. Then the third value, again 1 square divided by 9, then minus 1 square divided by 8 plus minus 1 square divided by 10. Therefore, this is how we are getting the contrast sum of squares. Therefore, once you do this calculation, then you will end up with the value for SSL equals to 3.81. Here we are defining this as contrast sum of squares. Even though it is contrast, we are using this L. It is because we are saying this contrast is a linear combination. Therefore, at the very beginning also, we have defined contrast using the letter L. Therefore, that is why we are using this as the letter L rather than seeing this as SSC. But anyhow, even though it is SSL, we are defining this notation as the contrast sum of squares. Therefore, for the above example, the contrast sum of squares is equal to 3.81. Then if you move to calculation of F value, calculation of F value, you can use the equation contrast sum of squares divided by mean square. Therefore, once you divide 3.81 by 0.1215, then you will get the calculated F value as 31.358. Now what you have to do is you have to check for the critical value, and then once you identify the critical value, then you have to compare the calculated F value with the critical value. Therefore, if you are going to identify the critical value, then it would be F. Here it is 1, and here this value should be n minus k. Therefore, if you go through this total number, then it would be 42, and there were 5 treatments. Therefore, you can get this value equals to 37. And once you check the previous ANOVA table, then you can see that this 37 was the error degrees of freedom. And now what you have to do is you have to identify this at the alpha level. Value of alpha is now 0.05. It is because the significance level was 5%. Then once you refer the table, F table, I have include the F table in the annexure 1, and if you move to that point, here what we have to do is, first of all, we have to identify the numerator degrees of freedom. This is numerator degrees of freedom, and the appropriate denominator degrees of freedom, it should be 37. Now once in this table the 37 is not provided, therefore the most closer value to 37 is 40. Therefore I will take this value. Therefore the value that I am considering as the critical value is 4.0847. Therefore now we will compare these values. Now if we compare these values, now you can see that using the annexure 1, we have obtained the critical value as 4.0847, and the calculated depth value was 31.358. Since the calculated depth value is greater than the critical value, then we have to reject the null hypothesis under the 5% significance level. Therefore, since we are rejecting the null hypothesis under 5% significance level, therefore, it can be concluded that the mean sulfur or the average sulfur content of coal seam 1 and 3 are significantly differ from the average sulfur content of coal seam 4 and 5. Therefore, we can end up with this conclusion, and this is how we are performing performing testing for contrast. And one other thing you have to keep in your mind, when you are defining a contrast, it should be meaningful. Now think about this contrast. Now think about this. Now you may have L equals, we are saying this L equals another contrast. We can say uh, here I am taking 3 times mu 2 minus mu 3 minus mu 4 minus mu 5. This is the contrast that they are providing us. Or if this is the contrast that one person has made, then first of all we have to identify what this contrast means. What this contrast means. As soon as you see this contrast, what you can say, 3 times the mean sulfur content of second coal seam, they are going to test whether the 3 times mean of the second coal seam are significantly different from the these coal seam 3, 4 and 5. Rather than saying it in that way, what you can do is try to isolate the uh, terms with the similar signs in one side and send all send the all others to the next side of the equation. Therefore, we will just forget about this L equals term for a while. We will just forget about this term for a while, and then we will consider about this part only. And here we are going to test this equals to 0. Therefore, what we can do is, first of all, I am keeping this 3 times mu 2 in one side, and I am sending all the other terms to the right hand side of the equation. Therefore, I can take this as mu 3 plus mu 4 plus mu 5. And then what I can do is, I can isolate this mu 2. Therefore, I can divide now both sides by 3. Therefore, I can take it as mu 2 equals mu 3 plus mu 4 plus mu 5, and this is now divided by 3. Then what we can do is, now there is somewhat a meaningful contrast. Therefore we can say that the mean sulfur content of coal seam 1 is equal to the average sulfur contents of coal seam 1, coal seam 3, coal seam 3, 4 and 5. Therefore, likewise you have to always build up a meaningful contrast. Therefore, we can define whatever number of contrasts, but these contrasts should be meaningful. Even though we are defining several number of contrasts, but those contrasts should be meaningful. Okay, now if you go through the next part, here we will discuss about the orthogonal contrast. So far we have discussed about a single contrast. So far we have discussed about testing for a single contrast. Now what we are going to do is, we are going to construct the orthogonal contrast. Therefore, now think about, if L1 is defined as summation of AI times mu I, where I goes from 1 to k, and L2 be another contrast where uh, summation of bi times mu I, where I goes from 1 to k. And now you can see that L1 and L2 are two contrasts. Therefore, we are saying that L1, the contrast L1 and contrast L2 are orthogonal if this condition satisfied. The condition is summation of ai times bi divided by ni, where I goes from 1 to k is equal to 0. It means that this, these coefficients and these coefficients, once you multiply the respective coefficients and divided it by the ith sample size, then if you get the summation of all these, then this has to be equal to 0. If this condition is satisfying, then we can say that L1 and L2. Therefore, this can be considered as the general condition. But the sample sizes are equal. If the sample sizes are equal, then we can say that L1 and L2 are orthogonal contrast if summation of AI times BI equals 0. It is because if the sample sizes are equal, then we can take this Ni out of this. Therefore, there is no any given meaning for Ni. Therefore, rather than using or rather than making the equation complex, you can use this type of simple equation to check whether the contrasts are orthogonal or not. Okay, now we'll consider an example. This is one example. Consider an Anova table where we are having k equals 5, having the equal sample sizes. Having the equal sample sizes and k equals 5 means here we are considering 5 treatments, and they have defined two contrasts L1 and L2. First contrast is mu1 plus mu2 minus mu3 minus mu5. Second contrast is mu1 plus mu2 plus mu3 minus 4 times mu4 minus mu5. Now what you have to do is you have to check whether these contrasts are orthogonal or not. Therefore, to check whether these contrasts are orthogonal or not, first of all you have to identify the AI values and BI values, and here we do not need to identify NI values. It is because they have given that we have to consider the equal sample size. Therefore, AI values, here we will get first value is 1, second value is again 1, third value is minus 1, and there is no any term with the fourth treatment. Therefore, for the fourth treatment, the value assigned for AI is 0, and for the fifth treatment, value assigned is minus 1. Then for the BI, I am taking the second contrast, plus 1, plus 1, plus 1, minus 4, and here we are getting minus 1. Therefore, once you multiply these, once you multiply these values, then here we are getting AI, BI values. Here we are getting AI, BI values. Therefore, what you need to take is, first of all, you need to take the multiplication of these two values, and then you have to add the values together. Therefore, once you multiply them, 1, here it is 1, minus 1, 0, minus 1. Therefore, this is what I have mentioned here. Then if you go through the addition of these five values, then you are ending up with this value as 0. Therefore, we can say that now L1 and L2 are orthogonal contrast for the given example. Now, if you are considering the same example with unequal sample sizes, you will consider the same example with unequal sample sizes. Therefore, the sample sizes are given as 20, 22, 24, 21, and 25. And we can show that the contrasts are not orthogonal. Therefore, what we have to do is we have to check for the summation of AI times BI divided by NI value. Previously, we have clearly identified what are the values for AI and BI. Now we have to take the value for AI, BI divided by NI value, divided by NI value. Therefore, AI, BI value then divided by NI. Here it is 20, here 22, third sample 24, fourth sample 21, and fifth sample 25. Now what we have to do is we have to add all these values together, then we can identify that the summation is not equal to 0. Then we can see that summation of AI into BI divided by NI, where I goes from 1 to k, does not equal to 0, then we can say that L1 and L2 are not orthogonal contrast. This is how we are identifying whether the contrasts are orthogonal or not. Okay. And when we are defining these orthogonal contrasts, it is not just the contrast, there can be many more number of contrasts, but we can identify this when we are defining these orthogonal contrasts. We can identify k minus 1 number of independent contrasts. It means that there should be only k minus 1 number of independent contrasts if we are identifying this orthogonal contrast. Therefore, if we are having this k minus 1 number of independent contrasts defined by L1, L2, L3 up to Lk minus 1, we have the property that the sum of or the square sum of the, if you consider the square sum of contrast, and if you take the summation of these square sums, it is the sum of square sums. Their sum of square sum is equal to the treatment sum of square. We can show it using a Anova table also. Therefore, if you are having if you are having k number of population, then maximum number of orthogonal contrast, independent orthogonal contrast that you can have is k minus 1. Therefore, if you sum up the value for the square sum of these k minus 1 independent contrast, then this value should be equal to treatment sum of squares. And now we will see how we can construct the orthogonal contrast. There are so many ways that we can define, but this is one method that we can easily identify the orthogonal contrast. First of all, we will see about for the three treatments. If we are having three treatments, definitely we know that there should be k minus 1 number of orthogonal contrast which are having independent contrast, or we can say orthogonal contrast. Therefore, three if there are three treatments, I can mention these three treatments in column wise, and since there are three treatments, there should be k minus 1 number of independent contrasts, orthogonal contrast. Then the k minus 1 is 2, therefore there should be only 2 contrasts. Since we are having 1 and 2, we will start from 2, and always the summation of a single row should be equal to 0. Therefore, if you consider this row, if you consider the first row, the summation should be equal to 0. Now you can see that 2 minus 1 minus 1. Therefore, what you can do is, first of all, you have to write down the treatments in the column wise and number of contrast in the row wise. Since you are having 2 contrast, you are starting here from 2. You are writing 2 here. Then to make this as 0, then you can place the remaining as minus 1. Then we are considering always the diagonal manner. Then what we have to do is we are keeping all the elements below the diagonal as 0. Therefore, here we will get the first value as 0. Then next value, here we have used 2. Then the next diagonal value should be equal 1. Then to balance this, or to make the row total into 0, what we have to do is we have to make minus 1 here. Then what you can define as the two contrast, as here L1 is the 2 times mu1. It is this is treatment 1 associate with mu1. Treatment 2 associate with mu2. Treatment 3 associate with mu3. Therefore, you can define the first contrast as 2 times mu1 minus mu2 minus mu3. And second contrast is mu2 minus mu3. Therefore, now if you check for these two contrasts, you can show that these two contrasts are orthogonal contrasts. And if you consider 4 treatments, as previously, first of all, you have to write the treatments in column manner and contrast in row manner. Always k minus 1 independent contrast should be there. Then what we can do is there should be 4 minus 1. Therefore, we can have 3 orthogonal, 3 contrasts. Then since we are having 3 contrasts, we are starting from 3. Then in the diagonal manner, we are keeping this as 2 and this as 1. All the elements below this diagonal, it is because here there should be another row. Therefore, if you draw the diagonal, then the diagonal should be in this way. Then the elements below the diagonal should be defined as 0, and the remaining can be kept as minus 1. Then 3, then to make it balance, then these values are said to be minus 1. Then 3 minus 1 minus 1 minus 1. Therefore, first contrast could be 3 times mu1 minus mu2 minus mu3 minus mu4. Likewise, the second contrast can be considered as 2 times mu2 minus mu3 minus mu4. The third contrast can be defined as mu3 minus mu4. But these are not the only contrasts that we can define. There are many more contrasts we can define. Now think about L4. I am defining fourth contrast as mu1 minus mu4. And I can make another contrast as mu5 is 2 times mu1 minus mu3 minus mu5. Likewise, I can make whatever number of contrasts, but if you check for any pair of given the first three contrasts, definitely these are orthogonal contrasts. Now, if you check with L1 with L2, then these two are orthogonal. Then L1 with L3, again orthogonal. Then L2 with L3, again these are orthogonal contrasts. But we can define many more number of contrasts for given set of population, but there should be k minus 1 independent orthogonal contrast only. Then for the five treatments, then for five treatment, we can define it in the same way. Now also you can define the orthogonal, this diagonal should be now starting from 4, since 5 treatments only 4 contrasts are there, therefore starting from 4, then next diagonal 3 2 1, and all the elements below the diagonal are 0, and then you have to balance, or you have to make the remaining elements as minus 1 just to balance the row total as 0. Therefore this is how you are getting the 4 orthogonal contrasts. These are independent because if you consider any pair of these treatments, any pair of these contrasts, then definitely these are act as the orthogonal contrast. That is the um, important thing, but you have to understand it here. There should be only k minus 1 independent orthogonal contrast. And in the previous one, we have defined that if we are having k number of independent contrasts, then the sum of squares of the sum of the square sum of these contrasts are equal to the treatment sum of squares. Therefore, this is one example we are considering. Here, the tensile strength of the synthetic fiber is used to make clothes for men's shirt in the interest of manufacturer. And it is suspected that the strength is affected by the percentage of cotton in the fiber. And they have identified 5 levels of cotton percentages, and they have defined it as 15%, 20, 25, 30, and 35 percentage. Therefore, for the easiness of calculation, I will take this as the fabric number 1, fabric number 2, fabric number 3, fabric number 4, and fabric number 5. This is just for the easiness of the identification of these fabrics. Therefore, based on the percentage of cotton in each fabric, they have identified as these are 5 fabrics, and from each of these fabric they have considered 5 units, and they have measured the tensile strength. Therefore, each of these fabric have 5 observations for the tensile strength, and they have given us the totals, or the treatment totals have given us. They have given us the treatment totals. Therefore, here this should be Ti dot. The notation should be Ti dot, not the Yi dot. Ti dot can be, it is the total. Okay, now they are asked us to construct the Anova table including the set of orthogonal contrast. Set of, actually this should be independent. There can be several, even several independent orthogonal contrast. Therefore, there can be many more contrast, but you just ask to contrast construct the Anova table including set of independent orthogonal contrast, and then as the next part they are asked to test for the each contrast under the 5% significance level and the interpret the result. This is what we need to do now. Okay, then if you go through the solution for this example, now you can see that here you can identify this is actually like a complete randomized design. It is because here we are having 5 treatments. For each given treatment we are having 5 observations. Therefore we can say this as a complete randomized design. Therefore, using the concept of complete randomized design, we can easily identify the values for these parts. Now think about for the treatment, for the error and for the total, you can identify the values as the degrees of freedom 4, 20 and 24, these SS values, MS value, and all these values can be calculated using the concept that we have defined under the theories that we have discussed for the complete randomized designing. Only new part of this would be identification of these 4 contrasts. Here I am going to only discuss about identification of these 4 contrasts. Okay, now what we have to do is, first of all, you are asked to construct the Anova table including the independent orthogonal contrast. Therefore, first of all, the Anova table should be built up using the standard procedures. First of all, you have to identify treatment, error, and total, and these values can be obtained. In the previous session we have discussed how we are obtaining these values if it is in a CRD form. Now we are asked to include the orthogonal contrast, independent orthogonal contrast. Since we are having 5 treatments, 5 minus 1 number of independent orthogonal contrast should be there. Therefore, altogether there should be 4 orthogonal contrast. Therefore, I have named them as L1, L2, L3 and L4. Then using the concept that we have defined previously in the previous table, we have defined on if there are 4 treatments, how to, if there are 5 treatments, how to obtain the contrast. Therefore, using this concept, I have created 4 independent orthogonal contrast. Therefore, these are the 4 contrasts which I have prepared or constructed, and now you can see that for each contrast the degrees of freedom is act as 1. Therefore, now you can see that for the first contrast degrees of freedom is 1, for the second 1, third 1, fourth also 1. And if you take the summation of these 4 degrees of freedom for the contrast, then this should be equal to the degrees of freedom of treatment. This should be equal to the degrees of freedom of treatment also. And the next thing is, now we need this is how we are defining or we are completing the column with degrees of freedom. Then we need to identify the sum of scarce values, scarce sum of values. Then we have to use this equation to obtain the contrast sum of scarce. Therefore, using this equation we can easily build up the contrast sum of scarce. Therefore, I will discuss the first contrast, calculating the SS values for the first contrast. Then what you can do is this SSL1, it is for the first contrast. Then the first contrast we can get the value CI is, if you see here, first C1 value is 4, then Y bar. Total we have obtained as, you can see the total is 49. Then what you can do is 49 divided by 5 is the 49 divided by 5 is the mean value. It is no need to have the decimal places at this point. It is because at the end of the calculation we will automatically get the values. Then next value is ci times y bar. Next ci value is -1. -1 times next total is equal to 77. Next total is 77 divided by again 5 observations. Then next one is again plus -1. Next total was 88 and it has to be again divided by 5. Then next ci value is -1. Total was 108 divided by 5 plus -1. Then next total was equal to 54. This has to be divided by 5 and then at the end you have to take its square term. And this complete part has to be divided by what? This summation of ci square divided by ni square. Therefore, we can take the summation of ci square as this first one is 4 squared divided by 5. Then plus -1 squared divided by 5. It is because sample sizes are now same. Then C3 value is -1 squared, then divide it by 5. C4 value is again -1 squared, divide by 5. C5 value is again -1, then its square term has to be divided by 5. Therefore, this is how we are calculating the contrast sum of square for the first contrast. Then likewise, you can calculate the SS value for second, third, and fourth contrast. Then for the first contrast, you have obtained SS value as 171.61. For the second contrast, 6.02. Third contrast 6.53 and the fourth contrast 291.60. Now if you add these values, if you take the sum of these square sums, then this should be equal to this 457.76. Now if you add this 171.61 and then 6.02, then 6.53, and next one is 291.60. Therefore, once you sum up all these values, this should be definitely 457.76. This is what I have explained previously in here. You can see in the note we are saying that the sum of the treatment, sum of the square sums of contrast are equal to treatment sum of squares. Therefore, now you can see it inside the Anova table also. Therefore, now you have to complete the next column. It is the ms column. The ss value would be equal to this ms value. It is because here contrast, the mean sum of contrast should be equal to contrast sum of squares divided by degrees of freedom. Since the degrees of freedom is equal to 1, then these two values should be equal to it. Therefore, ms values for contrast are same as the ss values. And this 8.06 we have obtained it previously. Now we have to calculate f ratio. To calculate the f ratio, we have to divide the ms value by the ms error value. Now 418.94 divided by 8.06, you can get this 14.76. If you divide, it is for the treatment, we have already identified it, but for the contrast, 171.61 divided by 8.06, then you will get this 21.29 value. For the second contrast, 6.02 has to be divided by 8.06 and the value would be 0.75. Therefore, in this form, you have to identify the F ratios. It is because these are said to be the calculated F values. It is because if you again go through the previous equation, the F value was calculated using SSL divided by MSE. Even though it is MSL, we are defining it as SSL. It is because this mean square value for contrast and the sum of squares for contrast are same. Therefore, you can use one of these to identify the F ratios. Therefore, the obtained F ratios has to be, this is for the first part, and in the second part they ask us to test for the contrast. Therefore, each F ratio value has to be compared for the contrast with the critical value. Therefore, in this example, you can see that n minus k altogether value of n is 25. We have altogether 25 observation. K is 5 number of treatments. Therefore, n minus k is equal to 20. Then you have to check for the critical value with f1 comma 20 at the 5% significance level. At the 5% significance level. If you check for this critical value, then you will obtain it as 4.3512. You can see it in the table also. In the table, degrees of freedom 1 and 20, it is 4.3512. This is the critical value you are obtaining. Then you have to compare the calculated depth values with this critical value. Therefore, now you can see that for the first contrast, calculated depth value was 21.29. Since this calculated value is greater than the critical value, we have to reject H naught. In the second contrast, calculated value is less than this F value, the critical value. Therefore, we are failed to reject H naught. In the third one also, we are failed to reject H naught since the calculated F value is less than the critical value. Here, in the fourth contrast, since the calculated value is greater than the critical value, then we have to again reject H naught. I told you that when we are having this 20, now if you see about this Anova table, here you can see that error degrees of freedom is also equal to 20. That is why we can say that n minus k. If you need, you can compute the value for n minus k, or else you can directly take the error degrees of freedom as the denominator degrees of freedom in this F critical value. Therefore, you can conclude or make your conclusion based on this decision. Therefore, it can be concluded that the mean tensile strength of fabric one, it is like the previous one. You have to identify what is the relation denoted by this given contrast. Therefore, mean tensile strength of fabric 1 is significantly different from average tensile strength of fabric 2, 3, 4, and 5 under the 5% significance level. But in the second one, we can say that there is no significant difference from the second fabric mean tensile strength of the fabric 2 with the average tensile strength of the fabric 3, 4, and 5. In the third one also, like previously, no significant difference. In the fourth one, we can have there is a significant difference in the tensile strength for fabric 4 with fabric 5. And this is one exercise that you can go through, and here the study is trying to identify the inflation of over 2 months time period and the inflation rates of these food categories have been identified. Therefore, here also they have considered 5 treatments, and they have given us they have replicated 10 times. It means for each of these treatment they will have 10 number of observation, and then the totals have given us for the first treatment, second, third, fourth, and fifth in this way. Therefore, Uh, First of all, you are asked to identify the experimental design to this problem, and then the partially completed Anova table is given. You have to complete the Anova table, and then you are asked to compare the inflation rates of fruits and vegetables with meat and dairy products. Therefore, you have to identify a suitable contrast uh, for this third part, and you can test for that contrast, and then you are asked to construct any meaningful set of contrast, any given. They are not asked to construct the orthogonal contrast. They are just asked to construct any meaningful set of contrast. Hmm. Then any meaningful contrast, and there will be the number will be vary. Therefore, according to your wish, you can identify the number of contrasts, and you are asked to test them at the 5% significance level. Therefore, as a practice, to practice this calculation, you can identify many more meaningful set of contrasts. And then in the fifth one, you are asked to construct a set of independent orthogonal contrasts. There should be independent orthogonal contrasts, and you are asked to test them under the 5% significance level. Okay, thank you all for joining with this session.